Hey everybody, and we're back. And now we are going to talk about Ohm's Law. So I'm going to go ahead and continue screen share, and then I will go ahead and show you on the whiteboard what it is that we'll go ahead and do. So real quick while I do this, Ohm's Law. So you might have heard of Ohm's Law before. If you read your chapter, you know for sure that you have heard of Ohm's Law. I personally believe that the book overcomplicates things a little bit. Let's just take it to its basis. What Ohm's Law will tell you is that it requires 1 volt of pressure to push 1 amp of current flow through 1 ohm of resistance. Essentially, that's how that law states. How you're going to figure it out is going to be via math. But it's fun math. It's not hard. It's pretty basic stuff. In the picture here, I've got a little pie chart, or if you look down below in this picture, it is what we call Ohm's Law pie chart. What your book, and I'm going to take you out of screen share here in a moment. What your book is essentially telling you is that you've got all these mathematical equations that you need to figure out here. So you've got stuff like E equals I times R, or R equals I over, screw that one up there, E over I, and so on and so forth. There's no need to memorize all of that. It's a lot more complicated if you try to think about it that way. If formulas are your thing or your jam, then get at it. Live your best life. Let me show you. Ohm's Law pie chart's a lot easier than having to memorize all of that. So Ohm's Law pie chart looks pretty much like this in your book. We've got pretty much a big pokeball, right? And up at the top, it says E, I, R. Let's make this a whole lot easier. As I mentioned, in your book, it likes to call voltage electromotive force. It likes to call amperage intensity, and R essentially is the easy one because that's our resistance. Here's what I'd like us from here on out to refer to this as. So I'd like our Ohm's Law pie chart, or pokeball, to be instead V up at the top, because that's what electromotive force is as we know it. A down here in the bottom left corner, because instead of intensity, we're just going to call it what it is, which is amperage. And then down here, we've got our ohms. We can use R if you want to, but this is going to be the Ohm's Law pie chart that we are going to use. Now, here's how you use it. This center or horizontal line down the middle is going to be a division line. Your old-fashioned division. Down the center here, going vertical, is going to be our multiplication line, meaning that anything in these 2 areas will multiply each other. Anything in one of these areas, or I'm sorry, 2 of these areas, whether it be voltage and amperage or voltage and ohms, they will divide. I'll go ahead and do a quick example here. So before I move on, if I have an Ohm's Law pie chart that says I've got 12 volts and I've got 6 amps. I've got 12 volts and I've got 6 amps. Well, I did mention this is our division line, right? So if I've got 12 volts, I divide it by 6 amps. 6 can go into 12 2 times. So that would give me, I can solve. If I know the amount of amperage and I know the amount of voltage in my system, then I can tell you how much resistance is in the entire system. Let's go ahead and do another quick example here. Let's say, let's go with 12 volts again, because we'll be working with that number quite a bit. And let's say I've got 3 ohms of resistance. Put that line back there. I've got 3 ohms of resistance, and I'm going to divide with 12 volts. So what it is I'm dividing this by this. So that means I can take 3 and shove it into 12 how many times? 4 times. So if you want to double check your math, you can. You can always multiply these two, and I should get 12, right? So 4 times 3 is going to give me 12. 3 times 4 gives me 12. If I don't know this number and I had 4 amps and 12 volts, I could divide it, and then it would give me 3 ohms of resistance. So you can sort of work back and forth. Ohm's Law pie chart essentially states if I know any two, I can figure out my third. If I know volts and ohms, I can figure out my amperage. If I know volts and amperage, I can figure out my resistance. If I know my amperage and resistance, I can figure out by multiplying, so remember that's our multiplication line, I can figure out my voltage. So if I want to do the same, we'll go ahead and clean this up a little bit here. Say I don't know my voltage, but I do know my amperage. Let's say I've got 3 amps and I've got 2 ohms of resistance there. Well, 3 times 2 is going to give me 6 volts, right? Because this is our multiplication line, this is our division line. So you may need to go back and rewind and sort of watch that again. If you have any more questions, just let me know. I am also thinking about doing Zoom sessions if needed. I know that I don't really have an SI necessarily for all my classes, so the ones that do, you guys will have an SI. For the ones that don't, I will try to have Zoom question sessions. So if you guys want to write down any questions that you might have, if you don't want to type them in the discussion board, I'll try to do a Zoom meeting. I know that right now, a lot of people doing live meetings are having a hard time right now. So anyways, neither here nor there, I will try to do live question sessions that if you'd like to participate in, you can. But that is Ohm's Law pie chart. We got volts, amps, and ohms, our division line, and our multiplication line. We're going to use this a ton. I'll talk more about this later. But that is our Ohm's Law pie chart. No need to memorize all of these other equations because they essentially reflect what Ohm's Law pie chart is. So if you can just remember the Pokeball and where the letters go, it's a lot easier. So we'll go ahead and screen share again. And let's see if it'll do it for me. Here we go, and we're back. So Ohm's Law pie chart. Okay, we just talked about that. You can see now what our bottom picture is really looking at. I've got a silly picture here on the left of kind of what each one is doing. You got the voltage that started shoving the amperage through the ohm of resistance. Just a silly picture, but that's your Ohm's Law pie chart that I just showed you guys. So let's go ahead and continue on. Now, realistically, what does a complete circuit need to have in order to work? So this picture here on the left is a really good example, but follow me here. So we have to have a power source. Why? Well, earlier I mentioned that your voltage needs to be the pressure, right? If we don't have any pressure, we have no electron movement, which is why if I was to measure the voltage across a metal table just sitting there, I'm not going to get any readings because there's no pressure pushing the electrons. Is it a conductor? Yes, but there's no reason for those electrons to move unless something pushes them. So we need a power source, which we know as a battery. So if we look at anything that requires electricity, we have some sort of power source. Our vehicle has a car battery, your remote has a AA battery, all the things that use electricity need to have a power source. If you're plugging something into the wall, we're using an electrical grid, right, from the electric company. That is our power source. It works a little bit differently, but that's not automotive. So what you guys can think of as a power source is going to be a battery. Now we need something to transfer those electrons and pressure from the battery to whatever it is we're trying to power, and that path is going to be called a power path. After I'm done explaining here, I'll go ahead and draw a picture up on the board. So we need a power path going to something. If we don't give electricity something to do, that electrical pressure and electrical current will create something to do. It's like a 2-year-old if you leave it alone on its own. If you don't give it something to do, it's going to find something to do, and it's probably not going to be good. In the case of electricity, if you don't give it something to do, it's going to create a whole lot of heat, which will create usually some sort of fire or melting of components, and it's never good. So we need to have an electrical load. And then from there, we need a path back to the battery. And I'll explain why here in a moment. That's called our ground path. You can call it a negative path if you want. But I need a full circle, a path from our power source to the load and our path from the load back to our power source. Now, it's always a good idea to have the last two in there. So the suggested circuit protection is going to be something like a fuse. It's going to protect the circuit from any sort of current spike. I'll explain how we get that later. But if we get a current spike past the point that our circuit can actually function at, believe me, there can be too much current flow. If I have too much electrons trying to go through, I'm going to have something bad happen. It's usually going to be way too much heat, which will either melt a wire, or if I have some sort of circuit protection in place, that circuit protection will break the circuit. And I'll explain how that works in a minute. And then we're going to have a switching device if you'd like. I mean, wouldn't that be nice if we could decide whether or not we wanted a light on or a horn to honk? Having any of those on at all times would sort of suck, and you question why you wanted that circuit. So a switching device is optional and pretty much always recommended simply for your convenience. Circuit protection is always suggested. However, I do not need either of those components in order for the circuit to actually work and do its job. So those are, essentially there's 4 things that a circuit must have in order for it to even try to do something. The last 2 are going to be suggestions or options depending on your application. And it's not going to the next slide. There we go. So we did just mention you need a circle, right? You need a circle of flow, and that's something called continuity. So I want to break the screen share here because I'm going to draw something for you. Okay, with my eraser here, I'm going to go ahead and start fresh. I'm going to draw our battery here. So this is our car battery. Everything's going to be car battery because that's what we're here for. We're here for automotive electrical. I've got my negative terminal. I've got my positive terminal. I need to, if I want a light bulb to light, we'll draw the light bulb. Let me draw the light bulb in, we'll draw it in green. I want a light bulb to light, right? So I've got a little filament inside my light bulb thread so I can screw my light bulb onto something. And I'm going to have 2 contacts. A light bulb, any basic light bulb is going to need at least 2 contacts. And those 2 contacts are going to be a power path, or a path from my power source, right? So I'm going to have a wire that's going to come from my positive. And in order for, right now, if I was to hook this light bulb up, it would not light. And the reason for this is because I have no continuity. Continuity is a constant path. Not necessarily constant flow, but a constant path for current flow. So I need a big circle. Not only do I need a path from my power source, but I also need a power path or a path back to my power source. We can call that a negative path. We can call it a ground path, whatever you want to. I need a wire that's going to somehow come back to my power source. If we're talking the actual electron flow, that means I've got a a path from my negative to the light bulb and then back to the positive. However you want to look at it, it doesn't really matter from a technician standpoint. What's important here is that if we're looking at this, let me get, I use all my colors. I'll use green again. If we're looking at this, that means I need to have a perfect circle for electrons to flow to my light bulb, through the light bulb, back out of the light bulb, and back to the power source. Amperage or current flow is going to be the same throughout my power source or throughout my circuit to and from the power source. We'll talk more about how that works in different types of circuits in a few minutes. But I need to have what this is. So what we've got is, I'll just draw arrows and then back. There must be the continuous path. So this big circle, if I don't have a continuous path, I don't have continuity. Let's say I have a break in the circuit anywhere. Could be here, could be here, could be a bad light bulb. If I have a break in the circuit, I have no continuity. That word should stick into your brain. Because if I have a break in the circuit, I can have no work being done. Like I said, whether that break is right here, whether that break is right here, whether that break is over here, it doesn't matter where the break is. If I have a break in the circle, I have no continuity. And if I go back to my screen sharing here, if I have no continuity, oops, here we are. If I have no continuity, then that means I have no work being done. I can't. No electron flow means no work being done. And I'll explain what voltage drop is in a moment, but I did mention that voltage is pressure. I did mention that amperage is current flow. Well, something has to get used up. There's always a trade-off. There's no such thing as a free lunch, right? So if I want a light bulb to light, something has to get used up. If I want a motor to turn, something has to get used up. If I want to heat something up, something has to get used up. So what gets used up in the circuit? It's going to be your pressure. So your pressure is going to get used up. I'm going to start with however much pressure or voltage my power source has, and then by the end, I'm gonna have no more pressure. In fact, physics says I can't have any pressure go back to the battery. It doesn't work. That doesn't happen. It's like fighting gravity, right? So if I have a break in the circuit, a break in this circle anywhere, then that means I have no continuity. No continuity means no electron flow because there's no path. If I have no electron flow, I get no voltage drop, therefore no work being done. And again, this is really something that's hard to do in a video that I'm not getting any feedback in. So if any of this is confusing you, please, again, ask questions in the discussion board. But I need you guys to understand that term continuity. Because if you don't understand that, you're going to have a hard time later on. It's one of those basic concepts that is so key into the rest of your learning in electrical. Understand continuity, understand voltage, understand amperage, understand ohms. So that's continuity. Now that we understand what all of those terms are now, let's get into one more term I need you to understand again. I know it's like, she needs so much from me, but I need you guys to understand some of this stuff. These are key fundamental topics that if you don't understand, there's always going to be a missing hole in your knowledge of electrical, and it's going to hold you back from being the diagnostician that you could. So there is something called ground, and everybody just thinks, oh, ground means negative. 9 times out of 10, you're right. But what the term ground is actually referring to is an uninsulated. So we know that our wires are covered, right? We don't have big bundles of just copper wire that are running together, or else the copper would touch each other. Conductors would send signals of voltage and amperage through different places that we didn't want. So if I press on my brakes or turn on my headlights, my horn honks, or everything else turns on, we don't want that. When I want my brake lights to turn on, I want just the brake lights to turn on. So we don't get that transfer of voltage and current flow. What we will do is we'll insulate the wires, right? So when you pull apart a wiring harness, you can see that each wire has a plastic or rubber coating on it, and they come in various colors. That is what we call insulation. Insulation protects, like I said, the conductors from transferring things that they shouldn't be transferring at that time. The term ground is referring to the side of the circuit that is uninsulated. Well, that's weird. Maybe you didn't realize before that we actually had a side that was not insulated. We do, and that is called a ground. So the term ground is also called common in many terms, in many other cases, especially in your book or in digital volt ohm meters. Instead of the term ground, we'll call it common, or negative, we'll call it common. Again, I know that it's sort of strange, and you're like, oh, aren't these negative and ground, is that the same thing? In all modern automobiles, essentially ground and negative are the same thing, because we don't insulate the ground side of the circuit whenever possible. And I'll explain why here in a moment. So if you look here in this picture that we have going on, we've got a battery that has a power path to the light bulb. The light bulb goes to this weird funky symbol down here where it's called body sheet metal or engine block. And then from the negative, we've got another connection going to that same symbol. What does that even mean? Well, real quick, pay attention to the symbols we've got here down in the PowerPoint. One looks sort of like a pitchfork. The other looks like a Wi-Fi symbol. The other one's an upside down triangle. They all mean the same thing, which is ground. And let me explain here what the heck that is. So I'm going to go ahead and erase this here. And what we'll do is I'm going to go ahead and draw my light bulb again. We got a little filament inside, some threads to screw the light bulb into. So I've got my power source and I've got a light bulb. And again, we must have a power source or a power path. In most cases, 99.5% of cars are going to have the the positive side as the insulated side of the circuit. So I'm going to have a wire that goes straight from my power source to the light bulb, and the entire way it's going to be insulated, and it's going to have plastic or rubber coating on it. On the other side of the circuit, here's what I can do. I can take a wire, and just like my old picture, I can take a wire straight from my negative side over to my light bulb. So now I have continuity, right? I've got a perfect circle of, or a perfect path for current to flow, right? Here's the problem. Cars would cost more and they would weigh a whole lot more if I had to have a wire going to every electrical component and a wire coming from every single electrical component. So here's how we can cut that down quite a bit. I can insulate one side of the circuit, meaning it's got a coating on every single wire and every single part of it that's going to protect it from touching any other conductors. And then on the other side, old Volkswagens used to do this on the positive side, but pretty much all modern automobiles are going to do this ground thing on the negative side of the circuit. What we do is I take the negative side of my power source and I will connect it to what we call ground. I'm going to use the Wi-Fi looking symbol as ground. What does this symbol mean? This symbol essentially means that it is this connection, or this symbol means a connection to either the vehicle body, the vehicle frame. If it's a unibody, obviously your body and frame are going to be one and the same. And then the last thing it's going to be connected to is the engine block. So body, frame, and engine, anytime you see this symbol, that's what it means that it's connected to. So this is going to be connected to the engine, body, and frame. Body and or frame. Now, here's what I can do. Well, since the body, engine, and frame, they all happen to be made of, what's that thing again? Metal. And we know that a lot of that metal is essentially going to be just as good a conductor as anything else. So why not use all of it as a conductor? And that's what car companies did. So instead of having a wire that goes, I mean, this could be at the very front of the vehicle, all the way to the rear of the vehicle, having to take a wire, go to each and every electrical component, headlight, brake light, horn, everything, and then another wire going back. What we did is we took the power source, connected our negative to the engine, body, and frame. That way, all I need to do is from the light bulb, connect anywhere on the engine, body, and frame, and we're using that as a conductor. So it's still, let me use another color here, it's still a continuous path through the engine, body, and frame. So we still have continuity, but I can significantly decrease the amount of wires that I'm using on everything. And so that's super nice. That saves, again, lots of money from car manufacturers, which again goes to the consumer. And then it's also going to save a lot of weight. Everything's always about gas mileage. And I mean, if you're trying to make horsepower, that's another thing too, right? So if we can cut the amount of wires that we're using to save money and weight, then obviously we're going to do it. And that's what grounds are. Could I connect a wire to and from everything? Absolutely. In fact, that's what hybrid vehicles do, because it's just too dangerous and high voltage and amperage to be able to use this ground system. Instead, they use what we call floating grounds, which isn't really ground at all. We have a power path and a negative path all the way to and from the battery with wires. They don't use the vehicle body and frame because it's too dangerous. If I was to accidentally touch it, then I could die. Now, again, I want to mention for body, frame, and engine, this ground connection must be bare metal. It can't travel through paint. It can't travel through any barriers in between. The connection must be to bare metal. So we will come back to that in a little bit, but I want to make that really clear. The electrons have a hard time traveling through anything that is not just the bare metal. So I can connect a light bulb to my power path and then to ground anywhere on the car. In the front of the car, in the back of the car, in the middle of the car, doesn't matter. As long as it's to a bare, and we call this, this right here is what we call chassis ground in the industry. Lots of people just call it chassis ground. And if you know what that means, then you know that it's me connecting the negative side to any part of the vehicle that is engine, body, and frame. So that's sort of a funky concept that not a lot of people ever take the time to talk about, but I always figured that that's something that's super important and needs to be explained. So that is what grounds are. I'm going to go back to our screen share here. And, okay, how do grounds work? So, again, the ground term is referring to the uninsulated side of our electrical circuit, which is why a lot of times on vehicles you will notice that there are these bare metal straps or cables that go from your battery to the vehicle's frame, or from the engine to the vehicle's frame. There is many of those connections, and if any of those grounds go bad, you can have all sorts of wonky problems. I always tell students, when you're having electrical issues where something's not working and you're getting voltage through the component, check out the ground, because so many times the ground is the problem. Moving along here. Circuit protection devices. I always have a little board that I have at school that I'll pass around, and you guys can see up close and personal what fuses and fusible links and circuit breakers look like, but I don't have it, so I'm going to share some pictures with you in this video here or in the PowerPoint presentation. But we've heard the term fuse before. We've all heard the term fuse. Maybe you've heard the term circuit breaker, because we all have them in our house. What do these components do? Well, first things first, I mentioned before that having too much amperage flowing through a circuit could be a big problem. It creates too much heat, which will usually result in some sort of fire or melting of components. So what does a fuse do? A fuse is going to protect the circuit from amperage spikes or from excessive current flow. And how does it do that? Well, fuses or circuit breakers or fusible links act as, and if we're looking at the computer here, a weak link. What we have in a fuse is something called a sacrificial element. So the sacrificial element is the weakest part in the whole circuit, and we do it on purpose because fuses are easy to get to, they're easy to change. So if I pop a fuse, it's no big deal. If I burn up an entire wiring harness, that could be lots of money. So what we do is we make the fuse weak, purposefully, weaker than any part in the circuit. That way, when I have an amperage spike, the fuse is the part that breaks, not burning up the circuit. And so here I've got examples of protection devices for circuits as fuses, fusible links, and circuit breakers. Fuses and fusible links are permanently damaged when they do reach their limit. So when I have a fuse that's rated at 15 amps or a fusible link that's rated at 40 amps, if I exceed that limit, then the fuse or fusible link will pop or blow, and it permanently disconnects. The part that is our sacrificial element will melt up, and it is no longer connecting the circuit. Well, if I have a break in the circuit, remember we talked about that, that means that there is no continuity. If I have no continuity, can I have any work being done? So that's what we're doing. We're purposefully breaking continuity so we don't damage the rest of the circuit. It's a fail-safe, if you will. Circuit breakers do the same thing. They're just a little bit nicer in the sense that they can reset. Most automotive circuit breakers are self-setting, so meaning they'll pass their limit of amperage, they will break the circuit, and once they have cooled down and the amperage flow has gone down, they will reconnect. A lot of times we'll use circuit breakers. Old timer turn signals use a type of circuit breaker. Your window regulator circuit will also possibly use a circuit breaker. Different types of circuits will use circuit breakers in automotive, but what you need to know is most automotive circuit breakers are self-resetting. The ones in your house are not, right? So if I plug too many things into an outlet, I plug an extension cord with a lot of outlets, and I plug in my blender and your hair dryer and your toaster and all the things, and you turn everything on at once, your circuit breaker pops, and all of them will turn off, right? So the circuit breaker pops open, there's no continuity, which way nothing works, and you got to go outside to your panel, and you've got to manually reset your circuit breaker. So that's how circuit breakers work. Let me go ahead and show you a couple of examples here. So we've got fuses, a bunch of different types of fuses, but on the left here, what your modern fuses look like. We've got little tiny ones that are called mini fuses or low profile fuses.
And in fact, actually, it's the wrong terminology. Instead of mini fuse here, it should say micro or low profile. Down here where the 3 is, it's called a mini fuse. The larger ones, which are pretty much some of the most common are going to be your mini or ATO fuses. And then the Ms.A fuses are going to be larger. They're going to be larger in size, and they're generally going to have the capability of a lot more current flow. On the right here, we have your glass cartridge fuses, where I've got a connection on one side as well as the other, and in the middle in the glass cartridge is what we call our sacrificial element. Down here on the left, you can see the sort of S-looking material in all of the fuses here. Down here in the ATO and the mini and the micro, all of them work the same. That little tiny element in the middle is our sacrificial element. That sacrificial element is the weak link that I was talking about. You can see on the left here, the Ms.A fuse says 40. That means that the amperage limit on that fuse is going to be 40 amps. Down here in the 15, they are color coded, by the way. So all your blue fuses are generally going to be 15. Your purple are going to be 3, and so on and so forth. There's tons of stuff online I can share with you guys on the colors of fuses. I'll definitely talk about it when we get back into class 2. So I've got color coding as well as a number up at the top that our fuse is limited at. Once the amperage flow reaches that limit and passes it, it will pop that fuse, and that little sacrificial element will burn up, melt, and break. And 99.9% of the time, it will break continuity and your circuit will not work anymore. These fuses generally don't break unless something has gone wrong in the circuit and you had an amperage spike. Once in a blue moon, you'll get a faulty fuse and that sacrificial element will blow simply because the fuse is faulty. However, most of the time, if a fuse blows, it's not the fault of the fuse. The fuse is a symptom, not the problem. The problem is going to be whatever caused the amperage spike. And remember back to that teeter-totter, the only way to make amperage go up is to make resistance go down. So for whatever reason, resistance in the circuit goes down too far, amperage goes up too high, your fuse pops. Don't think, oh man, these crappy AutoZone fuses just keep popping because they're so crappy. So that's just something to think about. Down here's a picture of a good fuse here on the right. So here's our sacrificial element. These teeth coming out are going to be where it connects into the circuit in your fuse box. On the left here, we can see that there's a sacrificial element that did melt up and is actually open in the middle. So there is no connection, no continuity, no worky, right? Fusible links do the same thing. They just look a little bit differently. They have connections in and out of the circuit. A lot of fusible links are rated pretty high. You got, 15, 20, 30, 40. This one here says 100 amps. In the center behind that number, there's a tiny little element you can see over here where my mouse is. That is our sacrificial element, and it does the same thing as a fuse. The fusible links can also, they come in different forms. So they've got ones that are completely uninsulated. They've got ones that, this one actually looks just like a wire, but instead it's a fusible link that's actually meant to burn up in the event of a failure. So fusible links do the same thing as fuses. Circuit breakers, like I said, do the same sort of job, except they don't get damaged and they're able to self-reset, at least in automotive. So on the right, this is what a lot of our circuit breakers in automotive will look like. If I was to pop this metal case open and look inside, this is what it would look like. So what you have is I've got 2 contacts. I've got an in and an out, right? And as long as everything's closed, electrons will flow through in and flow through out and then go to do whatever work, light, movement, whatever it is you're trying to do. If I get too much current flow, this connection here, this little board looking piece, that's actually going to be what we call a bimetallic strip, meaning it's made of different metals. And so what starts to happen, it's made of different metals that shrink and expand at different rates when they heat up. So when this little board piece heats up, it will warp. So it'll go from being flat to being bent up and warped. Once this little flat piece warps, it will no longer touch the outside of the piece here. So what we're looking at here is the electrons coming in, but once this board warps up, it's no longer going to touch. No continuity, right? Electrons can't make it out the other side. Once that bimetallic strip cools down, it will come back and make contact. And that's how circuit breakers work. I'll try to find some cool videos for you guys to post in the videos link on your module. And then lastly, you've got your control devices. I'm not going to get super into this because it's a simple switch. So when you are switching something to be on, you're closing it. No matter how your switch works, you are closing the switch or closing the circuit to provide continuity. When you open up a switch or what you might think of as switch off, you are opening up the circuit. No continuity, no work being done, no light, no heat, no movement, right? So that's what the circuit control devices is doing. You are either providing continuity or taking continuity away purposefully. And on the bottom here picture, I've got tons of different types of switches. You've got momentary contact switches that says push button. Switches can be normally closed or normally open, meaning that when you're not touching them, that's the state that they're in. I've got toggle switches that go back and forth. I don't want to get, like I said, into a ton of the control devices for any reason, because you're going to get into that in an electrical 54 class where you get a little bit more into the electronics of things. Just know that, sorry about the interruption, guys. Just know that a switch simply opens a circuit or closes a circuit whenever you want. That's what a control device is going to be. It's going to be whatever type of switch you're using. And before I get into circuit types, the last thing I want to talk about is what gets used up in the circuit and where it should get used up. So if we're looking at the picture here, we're using grounds, right? Here's our uninsulated side of the circuit on the negative side of the battery. And for a light bulb, we're using a ground to make the circuit whole, right? So it's a full continuity circle. We've got a fuse in the circuit, which, by the way, here in a moment, I'll talk about the different symbols for things that you need to know. That is the symbol for a fuse. This is going to be our symbol for a light bulb. And here's our symbol for the ground. What gets used up in a circuit is voltage. Like I said, that pressure is what gets used up. No matter what, your amperage is going to, your current flow is throughout the whole circuit. Where should I be using up voltage? Only where work is being done. So if a fuse is simply a conductor, that's a weak link, it's not really doing any work. It's not providing any heat. It's not moving. It's not making sound. It's not doing anything. It's just simply a conductor that has a limit. That's all. So you'll notice here, it's not using up any voltage across the fuse. My wires shouldn't be using any voltage unless something is supposed to be doing work. It shouldn't be using up voltage. Where voltage should get used up is going to be across whatever work we're doing. So if I'm lighting up a light bulb, I'm going to be using up voltage across that light bulb. I will have voltage coming in and either less voltage coming out or no voltage coming out the other side. That's how our circuits sort of work. Before I get into the types of circuits, I'm going to go ahead and start a new video here. So we'll go ahead and do that. Stop share. Real quick before I do that, I'm going to go ahead and show you some symbols that you should be using for stuff, just in case I use them or you see them in the future and you don't know what they mean. We'll try to make it easy here for you. So we've already determined that this symbol, our Wi-Fi symbol, is ground, right? And generally speaking our negative side of the circuit, but it's where our negative side of the circuit is uninsulated and is touching the engine, the body, and or frame, right? That's our ground. If I see a symbol that looks like a squiggly line, that is the symbol we're going to use for a fuse. Now, I did mention fusible link. Even though they do the same thing, they actually have a different symbol. So I just want to show you a very common symbol, and there's a couple different ones. I'll show you the common one. A common symbol for this one looks like a worm. That's actually poorly, let me try that one more time. A poorly drawn worm here. I just can't draw fusible links. It looks like a worm. That is our fusible link. And circuit breakers also have a symbol. This one's nice and easy because it looks like a banana skateboard. That would be our circuit breaker. And then from here on out, I'm going to be using these symbols on all the circuits I draw, so you're going to want to memorize these. The light bulbs that you guys are going to see, I'm not going to draw nice little snazzy light bulbs every time, because in your electrical wiring diagrams, they're going to look like this. So I'll have a wire coming in and a wire coming out, but this is going to be our light bulb. And I do have another one here. I'll draw in another color so it doesn't get blended up. Anything that has any sort of electrical resistance, I can draw, and I don't want you guys to get confused because this symbol right here is what we should know as a resistor. It's not anything that takes up resistance. If I have a light bulb, that could be it could be taking up resistance, but it's its own deal here. Resistors are actual components that all they do is they take up, they provide electrical resistance. And again, electricity has to do something. So how does it use up voltage without doing anything? It does. Resistors actually produce heat, but not enough to hurt anything around them. But that's how they get rid of voltage. And we'll talk about later on why you would want to use a resistor in a circuit. But if you ever see this symbol, it's referring to a resistor in the circuit, something that is purposefully taking up voltage or using up voltage in the circuit. So these are the really common symbols you guys might see. And last one is going to be your power source here. A lot of times you'll see a symbol that looks something like that. That's generally going to mean a battery, and I will show you that later in this presentation. So I will see you guys in the next video.